So today we're just going to cover the basics of motion in two-dimensional and three dimensions. And we're going to try to draw a link between the classical Newtonian model of classical mechanics and how it comes into play when we do vector calculus. So as with anything, the first thing to understand motion is to have like some preliminaries already set out. One of them is path. Path in simple words just means the place from where you go to where.
Is there a way to transfer the notes that you have
This
from there to another calculator?
is done with respect to time, time being one of our dimensions here, which basically helps us figure out at a particular time where I am. According to the classical Newtonian mechanics, velocity is described as distance upon time. So that is how, or the change in distance over the change in time. So, which basically means how much I traveled and what time I traveled, which basically gives you velocity. And lastly, acceleration is described as the rate of change in velocity per unit rate of change in time. So if there is an increase or a decrease in velocity, we say acceleration is increasing and decreasing. With this being said, in vector calculus, we kind of take a different approach where we start off with describing what we describe path first, but then we kind of go into acceleration to help us understand better. But to show the link between classical mechanics and the way that we do our problems in calculus, we are gonna do it the same route. So if at any time t, I am traveling from point A to point B, I can say that this can be represented by a function, let's say r vector of t. We said that the rate of change in distance per time was our velocity. The rate of change in calculus, we do it via differentiation. So if I was to take r of t and differentiate it with respect to t, this would basically give us the first order derivative of r prime, which can also be translated into being the velocity. And we said that acceleration was the change in velocity per time. So the change in velocity differentiated by time, or the second order derivative of our original path, can or not is our acceleration. Because we deal with 2 or 3 dimensions, just having a understanding of path as being by itself is not enough. Often in physics, we talk about point of reference. In a 2-dimensional space, understanding what is happening to a path is very important. For example, if I am taking a path that kind of looks like this, at every point in this path, I am doing something different. For example, all this distance that I covered here, I did it in a short amount of time. So my velocity is increasing. At this point, I change directions. And the rate of change becomes a little bit longer. So my velocity is decreasing. And so is my direction. And so on and so forth. So breaking things down into components becomes very important, it becomes very crucial. The way that I like to understand this is with an example of a pool table. If you have a pool table and you have a ball that you're trying to hit, but you don't have a straight shot, then you might start doing where you put an angle on that ball so that it hits the consecutive balls around it and everything goes in the direction that you want to. So in essence, what you're doing is at any point t, you are accounting for the changes that are happening in both x and y directions. So if I'm going super fast on the x direction and my y is going slow, that means I'm going towards the right, downwards, where I'm going very fast towards the right and very slow towards the down direction. To do this, to understand these directions, we use vectors. Two things that are very prominent in our calculus class is understanding the unit normal and the unit tangent vector. Basically, what unit normal and unit tangent vectors do is they help you describe two paths that are perpendicular to the point you're trying to calculate on. So if we take a path r of t and I want to find its tangent, then all that I do is find the derivative of it, which is also our velocity. So in essence, what I'm saying is velocity dictates my path. But because we're talking about a unit tangent vector, we need to normalize this. So this is what we end up getting. We end up getting the first order derivative of the path that we're taking divided by its own magnitude. If we just look at a regular graph, our normal is going to look, or is going to be the opposite reciprocal of our tangent. But just having that understanding is not enough. The normal unit vector is described as the first order derivative of the unit tangent vector divided by its magnitude. Because if a tangent is giving me a point that only strikes a curve at one point where it is perpendicular to the curve, the derivative of that is going to be tangential to the tangent itself, which through I forget the proof name, but in essence what we're ensuring is if we have a 90 degree here, then between the normal and the tangent there is a angle of 90 degrees, and that's what we're doing. And same as last time, we are also taking the magnitude and normalizing it with that, so we get a unit normal vector. So if you were to describe a path and you were to talk about what are the directions that are affecting it, you could use the unit normal and the unit tangent. The place where this becomes very important is when we start talking about acceleration, because path is deemed in the term of velocity in terms of acceleration, but there's nothing that we have that leads us backwards, which would help us describe acceleration. So we kind of use like a self loop and define acceleration with its components. So let's say I have a graph here. This time it's not going to be a RT graph, it's a VT graph, where velocity seems to be increasing and decreasing in this manner. If I want to find out the acceleration at any particular point, I am going to utilize the tangent and the normal to it so that I could get the relevant coordinates. So which means there is a certain scalar and a vector that's involved in describing these changes. In this VT graph, this can be done using a scalar acceleration tangential, scalar acceleration normal, and dotted with the unit tangential and the unit normal vector. And if we look closely, this kind of does a nice little thing where it basically gives you a graph where your actual acceleration, a sub t, is a line with a slope of 1. So then this gives us the Pythagorean, so through the Pythagorean theorem, we can say a sub t is equals to the scalar tangent times the unit tangent vector square plus squared. Through this, we can figure out any other relation that might be relevant. Something that's very difficult to do when you try to take a head-on approach to the unit normal vector is you're finding a second derivative to a first derivative divided by its magnitude, which can be a janky mess. So we utilize this to figure out what the normal would be. If we do that, then we come up with something like this. If we just talk in the terms of vectors, we have a sub t is equals to times t plus a sub n times n. Because our normal is made up of these components. We could find the scalar, because a sub t and the tangential vector is easy to find, we can always utilize the Pythagorean theorem to find the scalar, a sub n. So a sub n would basically just be magnitude of your acceleration at that point squared minus magnitude of the tangential scalar. Once you have this, you basically have all the information required to find the unit normal vector. And you can just apply vector, your acceleration vector minus the tangential vector divided by a sub n, which is our scalar, and that gives us the normal vector without having to do three order derivatives of a single function.